Epitaxy processes in semiconductor industry. Epitaxy is a foundational technique in semiconductor manufacturing, enabling the growth of crystalline layers on a substrate in a controlled manner. This process is critical for producing high-performance semiconductor devices. It begins with crystal growth, where atoms are precisely deposited in alignment with the underlying substrate lattice. This results in defect-free layers that are essential for reliable electronic behavior. The grown crystal layers form the basis of semiconductors, which are the building blocks for integrated circuits and microchips. These semiconductors are then used in electronics, powering everything from smartphones to advanced computing systems. Three key aspects define the epitaxy process. Layer growth ensures the controlled deposition of thin crystal films. Process control maintains optimal temperature and pressure, ensuring high-quality layer formation. Lastly, performance is enhanced through improved electron mobility, enabling faster, more efficient semiconductor devices across all applications. What is epitaxy? Epitaxy is a term derived from Greek roots, epi, meaning upon, and taxis, meaning ordered arrangement. Combined, epitaxy refers to the ordered growth above, which captures the essence of this process, building a crystalline layer that mirrors the structure of the layer beneath it. The simple definition of epitaxy is the controlled growth of crystalline layers on a substrate, where the newly grown layer adopts the atomic structure of the substrate surface. A helpful analogy is building with atomic-scale Lego blocks that must align perfectly. In the crystal growth process, a base crystal, known as the crystal substrate, serves as the foundation. The epitaxial layer is deposited on top, aligning atom by atom. Key inputs include heat, gas flow, and layer growth mechanics. Epitaxy was first developed at Bell Labs in 1951, marking a major milestone in semiconductor innovation. Why epitaxy matters in semiconductor manufacturing. Epitaxy plays a crucial role in advancing modern semiconductor technology by delivering benefits that go beyond what standard substrates can offer. First, higher purity is achieved through epitaxial growth, reaching levels like 99.9999%, something that's impossible using just substrates. This extreme purity ensures that electronic devices operate more reliably and efficiently. Second, enhanced conductivity results from the optimized crystal alignment in epitaxial layers, improving electron mobility and allowing signals to move up to 3 times faster. Third, epitaxy offers precise control over thickness and composition with atomic-level precision, within plus or minus 0.1 nanometers, ensuring uniformity across wafers. This leads to superior performance, enabling semiconductors to run at higher speeds with lower power consumption, up to 10 times faster and with 50% less power. These benefits make epitaxy a critical process for key technologies like mobile processors, RF devices, solar cells, and LEDs. Simply put, without epitaxy, modern electronics would not exist. Types of epitaxy. Epitaxy can be categorized into 2 main types, homoepitaxy and heteroepitaxy, each with distinct advantages and use cases. Homoepitaxy involves the growth of a crystalline layer using the same material as the substrate. For example, silicon grown on silicon. Because both layers share the same lattice structure, this results in a perfect crystal match, making it easier to process and offering higher reliability. This method is commonly used when consistency and structural integrity are essential. On the other hand, heteroepitaxy uses a different material for the epitaxial layer than the substrate, for instance, gallium arsenide, GaAs, on silicon. This introduces lattice mismatches, which can be leveraged to engineer strain and create novel properties. Heteroepitaxy offers greater material flexibility, enabling the development of advanced devices with specialized electronic or optical characteristics. Examples include GaAs on silicon or GaN on sapphire, which are used in high-speed electronics and LEDs. Types of epitaxy. Quick comparison. Epitaxy is categorized into homoepitaxy and heteroepitaxy. and understanding their differences helps guide process selection in semiconductor manufacturing. In terms of complexity, homoepitaxy is lower. It involves growing a crystal layer using the same material as the substrate, such as silicon on silicon, which minimizes strain and defects. This simpler structure supports applications like CMOS, complementary metal oxide semiconductor, and BJT, bipolar junction transistors, which demand uniform and reliable material quality. In contrast, heteroepitaxy is higher in complexity due to lattice mismatch between different materials. This mismatch often requires strain engineering or buffer layers to maintain structural integrity. However, this complexity allows for greater functionality, enabling advanced applications such as LEDs, RF, radio frequency devices, and solar cells. These technologies benefit from the unique electrical or optical properties introduced by combining different materials, even at the cost of more complex processing and integration. Major epitaxial growth methods. Epitaxial growth is essential for creating high-quality crystalline layers in semiconductor devices. 5 major methods dominate the field, each with unique strengths. MOCVD, or metal organic chemical vapor deposition, is a chemical process operating at high temperatures around 1000 degrees Celsius. It's cost-effective and the most widely used technique in industry, especially for LEDs and solar applications. MBE, or molecular beam epitaxy, is a physical process conducted under ultra-high vacuum, known for its exceptional precision, but comes with high costs, making it ideal for research settings. LPE, or liquid phase epitaxy, is a legacy technique with lower temperatures and simpler setups, but is rarely used in modern manufacturing. SPE, or solid phase epitaxy, operates at lower temperatures and is suited for specialized, limited-use applications. HVPE, or hydride vapor phase epitaxy, offers fast growth of thick layers, ideal for bulk crystal production. Each method serves specific industry needs. Key insight: choosing the right epitaxial growth method. When selecting an epitaxial growth method, understanding the trade-offs between cost and precision is essential. MOCVD, metal organic chemical vapor deposition, is the dominant choice in commercial production due to its cost-effectiveness and scalability. Its high throughput, relatively lower operational cost, and compatibility with mass production make it ideal for applications such as LED manufacturing and solar panels. In contrast, molecular beam epitaxy, or MBE, is preferred in academic and high-end research environments. Though expensive, MBE provides unmatched precision and atomic scale control, making it invaluable for developing cutting-edge semiconductor devices and novel materials. Ultimately, the method selection should be guided by the specific application's performance requirements and volume expectations. If ultra-high purity and layer accuracy are critical, MBE may be best. If scalability and cost control are key, MOCVD takes the lead. It's all about aligning the method to the end goal. Key process parameters and control. Achieving high-quality epitaxial growth depends on controlling a few critical process parameters. Temperature is foundational. MOCVD typically operates between 1000 to 1100 degrees Celsius, while MBE works at lower ranges from 500 to 800 degrees Celsius. The right temperature ensures optimal crystal formation. Pressure control is just as vital, often maintained at ultra-low levels like 10 to the power of -6 torr to prevent contamination and ensure purity. Gas flow rate also plays a key role. For example, hydrogen may flow at 1000 sccm, while trimethyl gallium might be just 20 sccm. Maintaining precise gas flow ratios is crucial to achieving the correct stoichiometry. Selectivity, which ensures growth only where intended, must be tightly controlled. Here, it's an excellent 98.5%. Finally, defect density must remain low. With a target of under 10 to the power of 4 defects per square cm, this process achieved 8.2 times 10 to the power of 3 per square cm. Real-time monitoring of these parameters is essential to maintain quality levels above 95%. Parameter interdependencies in epitaxial growth. Successful epitaxial growth requires precise coordination among several key process parameters, which are all interdependent. Temperature is the primary driver and has a cascading influence on the other parameters. Even small variations in temperature can shift reaction kinetics, alter gas phase dynamics, and impact deposition rates. Gas flow, for instance, determines the availability and concentration of precursor materials at the substrate surface. It directly affects the growth rate, uniformity, and material composition. Both temperature and gas flow ultimately impact the quality of the grown crystal, influencing factors like layer uniformity, defect density, and atomic arrangement. These three parameters, temperature, gas flow, and final quality, form a tightly coupled system. A slight deviation in one can disrupt the entire balance. Therefore, advanced feedback control systems are essential. Real-time sensors and automated adjustments help maintain optimal conditions, ensuring that all variables stay synchronized for consistent, high-quality crystal growth. Applications in semiconductor devices. Epitaxial growth plays a transformative role in the performance and capabilities of today's semiconductor devices. In LEDs, epitaxy enables precise color control through accurate wavelength tuning, supports up to 90% efficiency, and ensures high crystal purity with minimal defects, making it the industry standard used in 85% of devices. For solar cells, epitaxy improves light absorption by tailoring band gaps and delivers over 45% conversion efficiency in advanced designs. It also supports multi-junction configurations, where layered structures significantly boost power output compared to traditional cells. In transistors, epitaxial layers enable ultra-fast gigahertz operation, reduce power consumption, and allow for extreme miniaturization down to 3 nanometers, resulting in performance that's 10 times better than bulk silicon. Lastly, integrated circuits benefit through epitaxy's support for massive integration, diverse functionality, and the development of innovative architectures. These advancements collectively drive higher performance, energy efficiency, and complexity in modern electronics. Applications in semiconductor devices. Epitaxy plays a foundational role in enabling modern semiconductor devices by offering both precise control and enhanced performance at the atomic level. In an epitaxial device structure, layers are grown sequentially, starting with the substrate, followed by multiple epitaxial layers, and topped with a contact layer. This allows atomic-level thickness control, critical for device miniaturization and consistency. Epitaxy also provides precise composition control, enabling engineers to tailor materials for desired electrical or optical properties. High-quality interfaces between layers are essential to reduce defects and ensure reliability. The results are compelling: higher device efficiency, improved electrical performance, and significantly fewer defects. These benefits support high-end applications across industries. For instance, the LED market alone reaches $45 billion. In solar, epitaxy enables up to 95% efficiency. At the leading edge, it supports advanced 3 nanometer nodes and over 100 billion transistors per chip. Epitaxy is the key to scalable precision and performance. Benefits and advantages. Epitaxy offers transformative advantages in semiconductor manufacturing by elevating material quality, precision, performance, and cost efficiency. First, material purity is a major benefit. Epitaxial layers can achieve purity levels of 99.999%, making them 10 times purer than bulk materials. This ultra-high purity supports defect-free crystal growth, which is critical for advanced devices. Next, epitaxy delivers precise control at the atomic level. With thickness control down to +1 angstrom and 100% uniformity, manufacturers can achieve monolayer precision, ensuring consistent and reproducible results across wafers. This level of control leads to significantly enhanced performance. Compared to bulk materials, epitaxial layers enable up to 3 times better efficiency, supporting high-performance, energy-saving applications. Finally, epitaxy is highly cost-effective, with ROI metrics showing 300% returns and 40% cost reduction. The long-term savings are substantial. Lower defect rates also reduce waste, making epitaxy not only a performance enabler, but a sustainability and economic driver as well. Epitaxy versus conventional methods. Comparing epitaxy to conventional semiconductor methods clearly reveals substantial advantages across every critical metric. First, material purity improves from 95% in conventional techniques to 99.9999% in epitaxial growth. While a 5% difference may seem small, it significantly impacts electronic performance by enabling ultra-pure crystal formation. Defect density sees a dramatic improvement, dropping from 107 defects per square centimeter to just 104. That's a 1,000-fold reduction in defects, translating to better yields and more reliable devices. In terms of performance, epitaxial layers provide a 3-fold improvement over standard materials, boosting energy efficiency, speed, and signal integrity in high-performance applications. Finally, cost efficiency may appear counterintuitive, dropping from 100% to 60%, but this reflects the upfront cost. Despite that, long-term cost reduction is realized through fewer defects, improved yields, and less rework. Altogether, epitaxy delivers superior purity, lower defect rates, enhanced performance, and improved lifetime cost efficiency over traditional manufacturing approaches. Transformative impact on industry. Epitaxy is revolutionizing semiconductor manufacturing by delivering unmatched improvements in material quality, device performance, and production economics. One of its most important contributions is crystal quality. Epitaxial growth achieves 99.9% crystal quality, meaning near-perfect atomic alignment for exceptional reliability and electrical performance. This high purity and structural order lay the foundation for better devices. In terms of performance, epitaxy offers a 10x gain compared to traditional bulk or diffusion-based methods. Devices become faster, more energy efficient, and capable of supporting advanced logic and analog functions. Just as important is cost reduction. Epitaxy can reduce manufacturing costs by up to 50%, driven by fewer defects, higher yields, and minimized rework. These benefits explain its widespread use. With 95% adoption across the industry, epitaxy has become a cornerstone of modern semiconductor fabrication. The bottom line, epitaxy provides the breakthrough performance, quality, and cost-effectiveness needed to power next-generation electronic technologies. Challenges and considerations. While epitaxy delivers unmatched advantages, it also comes with significant challenges and considerations that must be managed. The first is technical complexity. Epitaxial processes demand atomic-level precision, making them extremely difficult to control. Thickness must be regulated within plus or minus 1 angstrom, and temperature must remain stable within plus or minus 1 degree Celsius. These tight tolerances require advanced hardware, real-time monitoring, and expert-level process control. As a result, the difficulty level is categorized as extreme. Even small deviations can lead to a high process failure risk, estimated at 15%, which can result in defective wafers, costly rework, or material loss. Additionally, the high investment cost is a major consideration. Initial setup for epitaxial equipment exceeds $5 million, making it one of the most capital-intensive processes in the fab. On top of that, annual maintenance costs can reach $500,000. Together, these technical and financial demands make epitaxy both a high-risk and high-reward strategy in advanced semiconductor manufacturing. Challenges and considerations. In epitaxial manufacturing, there are 2 major barriers to success: quality control and skilled expertise. Quality control is critical due to zero defect tolerance in this process. Any irregularity in testing, analysis, or correction stages can severely impact yield. The typical yield loss due to inadequate quality control ranges from 20 to 30%, making it one of the most significant cost drivers. On the other hand, The process requires deep scientific understanding and practical expertise. Most roles demand 2 to 3 years of specialized training, and in many cases, a PhD-level education is required. Unfortunately, this leads to high talent scarcity in the field. To address these challenges, proven solutions include phased investment strategies, the use of AI automation for better accuracy, real-time monitoring to catch issues early, and robust training programs to build and maintain expert-level capabilities. Industry Challenge Overview. Epitaxial manufacturing presents a set of high-stakes industry challenges that must be carefully managed. First, the initial setup investment is substantial, ranging between $2 million and $5 million. This capital covers equipment, infrastructure, and process development, making it a significant barrier to entry. Once the system is in place, workforce training becomes critical. On average, operators and engineers require 6 to 12 months of intensive training to reach competency. The process itself demands a high degree of precision, with a minimum quality requirement of 95%. This means that even small deviations can lead to failure, rework, or yield loss. Despite these challenges, the success rate across the industry remains relatively high at around 80%. This indicates that while difficult, success is achievable with the right combination of investment, training, and process discipline. Future outlook and summary. The future of epitaxial technology is both transformative and promising. At its core is atomic-level precision in crystal growth, enabling unmatched structural control. Multiple deposition methods, like MOCVD, MBE, and LPE, offer flexibility depending on material and application needs. These processes consistently achieve superior material purity, with 99.9999% purity already realized. Additionally, advancements have led to significant cost efficiency, with reductions of up to 40% compared to traditional techniques. Today, epitaxy is widely adopted across the semiconductor industry, with a 95% adoption rate, making it an established standard. Looking ahead from 2024 to 2030, 3 emerging trends will shape growth: AI-driven process control for optimization via machine learning, green manufacturing emphasizing sustainability, and exploration of novel materials beyond silicon. Market projections also indicate strong momentum, growing from $12 billion in 2024 to an estimated $35 billion by 2030, signaling robust global demand and continuous innovation. Technology Roadmap: the path forward. The future of epitaxial technology is mapped out across 4 critical development phases, highlighting its transformational journey. From 2024 to 2025, the focus will be on enhanced automation and integration of artificial intelligence. These advancements aim to improve process efficiency, consistency, and predictive control across production lines. Moving into 2025 through 2027, the industry anticipates breakthroughs in quantum materials, which will redefine the capabilities of semiconductors beyond classical limitations, opening doors to entirely new performance regimes. By 2027 to 2029, the goal is global-scale deployment. At this stage, epitaxial solutions will become more widespread across fabs worldwide, making advanced devices more accessible and production more scalable. Finally, from 2030 onward, we will enter the era of next-generation devices, applications leveraging the full potential of AI, quantum engineering, and novel architectures. This roadmap reflects a future built on innovation, scale, and intelligent manufacturing.